Welcome to Rust for Windows, a new series for Windows developers wanting to learn how to make the most of Rust on the Windows platform. My name is Kenny Kerr, and in this second installment, I'm going to introduce some of the individual crates published as part of Rust for Windows. At the highest level, there are essentially two general-purpose crates that provide access to Windows APIs. Part 1 of this video series already introduced the Windows crate and how you can use it to easily call virtually any Windows API. Then there's the Windows syscrate that provides raw bindings for the Win32 subset of APIs only. The Windows crate provides everything from WDK, Win32, or C-style APIs, COM APIs like Direct3D, as well as WinRT APIs. If you're just exploring your options, that's probably a good place to start. The Windows syscrate provides all the C-style APIs, but lacks any that require COM support. More generally, the Windows syscrate avoids any wrapper functions as much as practical, since function bodies happen to be the most expensive thing for the Rust compiler to deal with as far as build time is concerned. Hopefully that will change in future. So the Windows syscrate lacks any COM support because COM necessarily requires functions to emulate the virtual dispatch that the C++ compiler naturally provides and upon which COM is built. The distinction between the raw functions and wrapper functions can also be seen in how Win32 or C-style APIs are exposed across the two crates. Both crates, for example, provide the bcrypt cryptography API. Calling the bcrypt gen_random function using the Windows syscrate with the raw bindings would look something like this. We're opting for the system-preferred RNG algorithm, so a null mute is used to indicate that no algorithm is provided. The buffer is provided as a mutable pointer and length separately. And finally, you have to deal with errors somehow. Pretty straightforward, but requires a bit of work to call directly, as it maps directly to the function exports from the bcrypt DLL provided by the operating system. Now contrast that with the same call written using the Windows crate. Here, none means no explicit algorithm is provided, a much more natural way of expressing this in Rust. The buffer is provided directly as a mutable slice, taking care to check for integral type conversion. This is obviously way simpler and way harder to get wrong. Finally, complete error handling, conversion, and propagation is provided out of the box. Once compiled, the results are the same. We've just had to write a lot less messy code ourselves, which is obviously a lot less error-prone. Still, at scale, all these wrapper functions can add up, so you need to balance the benefits with the potential cost to your build time. On the other hand, it's practically, if not technically, impossible to call virtual functions as required by COM and WinRT without some kind of wrapper, so that's left to the Windows crate. The Windows syscrate doesn't attempt to handle those for the sake of keeping its size and build time to a minimum. Another way to look at this is the size of the Windows crate and Windows syscrates on crates.io. Quite the difference. Here's the Windows crate clocking in at around 9 megabyte, and Windows sys at under 3 megabyte. Translated into lines of code, that's around 280,000 for Windows sys and 2 million for the Windows crate. Now the crate size doesn't really matter all that much since those crates are all compressed and cached. It's more about the actual lines of code that must be compiled. That's why these crates also use features to limit what exactly is included and compiled by default. Here's the cargo toml file for the Windows crate. You can see it has a number of features that it provides. It basically prevents all of those many thousands of lines of code from being compiled unless you specifically need APIs from the various features. If all you need is the threadpool API, then just include the Win32 system threading feature and build time will be kept to a minimum. Each of these features maps directly to a Rust module. Well, there's a lot more we could say about these two crates, but let's leave that for the moment and explore some of the other crates that are available as part of Rust for Windows. I've already hinted at one, and that's the Windows targets crate that both the Windows and Windows syscrates use to handle imported functions. The Windows targets crate takes care of a difficulty that is somewhat unique to Windows, but also compounded by Rust language design. You may notice that whether you employ the Windows crate or the Windows sys crate, you automatically get a dependency on the Windows targets crate. This crate provides universal linker support for Windows APIs. The Windows targets crate includes import libs, supports semantic versioning, and optional support for raw dylib, the future of linking in Rust. You can target the usual suspects with MSVC, GNU, or LLVM, meaning you can use any of those targets and toolchains to build and link binaries for Windows. An import lib contains information the linker uses to resolve external references to functions exported by DLLs. This allows the operating system to identify a specific DLL and function export at load time. Import libs are both toolchain and architecture specific. In other words, different lib files are required depending on whether you're compiling with the MSVC or the GNU toolchains, and whether you're compiling for the x86 or ARM64 architectures. Note that import libraries don't contain any code, as static libraries do. While the GNU and MSVC toolchains often provide some import libs to support C++ development, those lib files are often incomplete, missing, or just plain wrong. This can lead to linker errors that are very difficult to diagnose. The Windows targets crate ensures that all functions defined by the Windows and Windows sys crates can be linked without relying on an implicit lib file distributed by the toolchain. This ensures that dependencies can be managed with cargo and streamlines cross-compilation. The Windows targets crate also contains version-specific lib file names, ensuring Semver compatibility. Without this capability, the linker will simply pick the first matching lib file name and fail to resolve any missing or mismatched imports. So this all happens automatically when you use the Windows or Windows sys crate. But did you know that you can use it directly if needed? Sure thing. Let's start by adding a dependency to the cargo toml file like so. You'll notice that this project has no other dependencies. Now in the main source file, we can use the link macro provided by the Windows targets crate to define the external functions we wish to call. That's the set lost error function from kernel32.dll. And get lost error. And then we can take them for a spin. These are unsafe functions. We'll set the current error. And print it out. And that's all there is to it. And you can see how Cargo automatically downloads and compiles the Windows targets crate. All available targets are added to the lock file, but only the 64-bit MSVC target is compiled, since that's the default on my machine. And sure enough, the lost error is what you'd expect. By default, the link macro will cause the linker to use the bundled import libs. Compiling with the Windows raw dylib Rust build flag will cause Cargo to skip downloading the import libs altogether, and instead use raw dylib to resolve imports automatically. Let's give that a try by creating a cargo config file for the project. This just lets us override project build defaults and something called Rust flags. And we'll specify a custom config flag called Windows raw dylib. And now let's see what that does. I'll use cargo clean to erase build artifacts so we can start over. And then cargo run to build everything from scratch. Notice how it builds Windows targets, but no target or architecture specific crate is included at all. In this case, the link macro, here in the main source file, this link macro takes care of everything. It employs a newish Rust compiler feature that instructs the compiler to generate the import entries directly. Thanks to the macro, this works without you having to change any of the code. Without the Windows targets crate, switching between linker and raw dylib imports requires very intricate code changes, since the Rust compiler requires very different import code to be written for different calling conventions, target architecture, and whether or not you're using import libs or the raw dylib feature. So that's cool, but obviously doesn't scale to the myriad APIs provided by Windows. Is there a middle ground somewhere between writing all of these imports by hand and the large prepackaged and all-encompassing API crates like Windows and Windows Sys? Well, as it happens, there is. Believe it or not, I didn't write those crates by hand, all 2 million plus lines of code. Nope, I wrote a code generator, and that same code generator can be used directly to generate bindings for just the APIs you need. Obviously, this is going to be a little more involved and require a bit more hand-holding than simply adding a dependency on the Windows crate. But sometimes that can come in real handy. This can also help to reduce your dependencies while continuing to provide a sustainable path forward for any future API requirements that you might have, or just to refresh your bindings from time to time to pick up any bug fixes automatically from Microsoft. Back in the cargo toml file, alongside the Windows targets crate, let's add a second dependency on the Windows bindgen crate. The Windows bindgen crate is only needed for generating bindings and is thus a dev dependency only. You can, of course, use it in whatever way makes sense to you. It's just a library crate. You may, for example, use a different crate to generate bindings, a build script, or any other approach. Here, let's just use a local test to keep things simple. The Windows bindgen crate provides a single function called bindgen that accepts any number of string arguments. We might structure it as follows. Naturally, it provides basic error handling to help you figure out what went wrong with the arguments. But they behave much like command line arguments, so you should quickly get the hang of it. Let's see if we can get it to generate these two functions, getLostError and setLostError, that we previously wrote by hand. First, we'll need to filter them out, so to speak, as there are thousands of APIs to choose from. Filtering is quite powerful, but for now, let's be explicit and call out the two we need. setLostError and getLostError. We'll talk more about where these paths or namespaces come from at a later stage. We can then tell bindgen where to write these bindings. And then finally, there are some config options to generate the appropriate bindings to match what we wrote by hand. Be mindful that Windows bindgen is a powerful tool, and it has some sharp edges at this stage, so you can generate code that won't necessarily compile. If you're unsure, just use the Windows or Windows Sys crates. Anyway, let's run this test quickly. And you'll notice here in the Explorer panel, there's a new bindings.rs file in the source folder. Let's open that up, and wouldn't you know, they are the two functions we previously wrote by hand, and they look largely the same. There's more going on here, but not much, and you can probably guess what that's about. Now back in the main source file, we can switch to using the generated bindings simply by removing the handwritten code and declaring the bindings module, and adding a use declaration for convenience. And let's take it for a spin. And just like that, we're using generated bindings, a much more scalable approach, if a little more work than using the Windows Sys crate directly. So whether you prefer using the Windows, Windows Sys, or Windows bindgen crates, Rust for Windows has you covered. but there's much more to discover and learn about Rust for the Windows platform. We'll explore it all in due time, so stay tuned for more in this new series on Rust for Windows. Until next time.